Okay, so let's quickly look at these questions. This is actually a question from an exam paper that is that almost questions all of the things we've just quickly looked at. So first of all, what is the definition of a strong acid?
An acid that dissociates completely.
Good, an acid that dissociates completely. Good. A solution of an unknown, look at this, monoprotic acid. I have no idea what that means. Okay, doesn't matter, I don't need to know. Has a concentration of, okay, now they give me the concentration of the acid and they give me the pH. Now they ask me to calculate the concentration of the hydrogen ions. Okay, so what is my pH formula? Okay, OH or just H? H plus. OH and H plus would be the same. Okay, so we want to find that value, which means we just substitute in here. We have a pH of 3 is equal to negative log. You know, a log is base what? If there's nothing?
10.
Base 10. Okay, and we want H plus. And now we just solve this. So put this back into exponential form. So this means just get rid of the negative first. So multiply the negative on the other side. Okay, so that now we have 10 is equal to the concentration of H plus. Now if you just go and do this, this means the 10 to the power of negative 3 is 0,001 mole per cubic decimeter. Now look at this. Look at the concentration that it had. That's the concentration of the acid. And look at the pH. Is the concentration of the hydrogen ions more or less than the concentration of the acid?
It's less.
It's less. Does that mean it dissociated completely or not?
It means it dissociated.
But did it dissociate not completely? Because if it dissociated completely, then this would have been the answer here. Okay, does that make sense? Okay, if it dissociated completely, if it did not dissociate completely, then the concentration of hydrogen would be less. Okay, because there's still then a little bit of acid in that concentration left. It didn't completely dissociate. How will the strength of the unknown acid compare to that of hydrochloric acid? Is hydrochloric acid a strong or a weak acid?
A strong one.
It's a strong one. So if it was 0.01 hydrochloric acid, what would the H plus have been? If it was 0.01 mole per decimeter hydrochloric acid and it dissociates completely, what would this have been? 0.01. That's the thing about a strong acid, is the concentration of the acid would equal the concentration of the hydrogen or hydronium. Okay, makes sense? So compared to that, is which one is the stronger, this unknown acid or the hydrochloric acid? Hydrochloric acid is stronger. Okay, give a reason for your answer. Because hydrochloric acid would have dissociated completely and therefore have this concentration. Ammonium chloride, that is NH4Cl. Ammonium chloride is an example of a salt that can undergo hydrolysis. Okay? Define the underlying term. What is hydrolysis?
It's dissociation of salt to produce a weak acid or base.
Okay, dissociation of salt in water. Yeah, that's where the hydro comes from. Dissociation of salt in water to produce a weak acid or a weak base. Okay, now we have to write the equation. Before we before we're going to write the equation, okay, well, let's write the equation. So we will have NH4Cl plus, not plus, but just dissociates in water to NH4 plus Cl. Make sense? Okay, it's 3 marks. I don't know if I did all of that. Okay, but that is the dissociation equation. Okay, the next thing, however, is they ask us now if methyl orange is red in acidic, yellow in an alkaline medium. What will the color be of methyl orange? So we need to know what two acids produced, what acid and what base produces this salt? Because remember our little table, weak acid, strong acid, weak base, strong base. Okay, so it would probably not be that one, because then I need to calculate Kb, and this is just a two-line answer. Okay, so but for strong acid, weak base, it would be acidic. Strong base, weak acid, it would be basic. Strong base, strong acid, it would be neutral. Okay, make sense? So we want to know, was it a strong acid? Okay, so which two produced this? NH3. That is a acid or a base? That's a base plus HCl. Hydrochloric acid. This is strong or weak? Strong. This is a base. Strong or weak? Okay, you need to go and study the strong and weak ones. I gave that earlier. So strong. This is a weak base. Okay, strong bases always have an OH at the end. Okay, and a weak base and a strong acid, so it would be acidic, which means what color will it be? Orange. Red, sorry. Methyl orange is red. Okay, make sense?
Yes, it does.
Thank you. Okay, let's now quickly look at this ridiculous question. I'm going to copy and paste it here, so we can do it together. Some space on this side. There we go. Okay. A learner adds a sample of calcium carbonate. Okay, they give us the amount. Adds a sample of calcium carbonate to, and they give us a volume of sulfuric acid. The sulfuric acid is in excess and has a concentration. So we have too much of sulfuric acid, and we know what its concentration is. Okay? In the balance equation, and now what happens is that the reaction is allowed to proceed until so look now, what's the problem? If I draw it, so we're adding our base. Okay, I'm dripping in an unknown concentration of calcium carbonate. Okay, into a known concentration that's in excess. And you see, this is exactly opposite that I said before. Okay, so okay, so we'll go through it, and then you'll see. You can see it's 10 marks. It's quite a big question. So, but if we go on, so we know the concentration and the volume for H2SO4. They give us, that's very kind of them, they give us the reaction. You can see these two produce a salt, and it produces carbon dioxide, which is going to escape in the form of gas, and it's going to produce water. So this is going to be a salt solution, but the sulfuric is in excess. So after I've added all of the calcium carbonate that I could, there's still sulfuric solution left. Okay, which means this is not neutral yet. Okay, so now they go ahead and they say the reaction is allowed until all of that is used up. Now there's some of this left over from reaction 1. This is now neutralized. In other words, they're going to add something else now by this much sodium hydroxide. So now we add, in a new experiment, we take what is left over from this and we add now, okay, sodium hydroxide, NaOH. And of the sodium hydroxide, we know the volume as well as the concentration. So volume is known, concentration is known. Do we know the concentration here? No, we knew what it was in the beginning, but now we don't know how much it is now. So concentration is unknown. We still know the volume though. Okay, there's still 50 cubic centimeters. Okay, all of that was used right here. Make sense? Okay, but in the solution, there's now less. The concentration is less now because some of the sulfuric acid has reacted to form salt. Okay, makes sense so far? So just look at the second. We're going to have to work backwards. Okay, we first have to find the the amount of moles that was left after this one. If we know how many moles there was before we neutralized it, then we know how many moles was used by this. If we know how many moles was used here, we can see how many moles was in here, because for every 1 mole used, 1 mole was added. Or for every 1 mole reacted, it was because 1 mole was used. Okay, and so we're going to do this backwards. So again, we're going to first calculate in this reaction. Just look what they ask. They ask you for the mass of calcium carbonate. So in the end, they want the mass. We know mass is equal to the moles times the molecular mass. Okay. Sorry?
The big mass.
The big mass. Good. Okay, so we want big mass we get from our periodic table. We want moles. We want to know how many moles was there in here originally. Okay, and the amount of moles that was in here originally is the same amount of moles that reacted here. Okay, so let's go through that. So we're going to look at the bottom one first. In the bottom one, we see that we have in this equation, we have that the reaction, I suppose you can use your rice table, but the ratio is important. The ratio here is that acid to base is equal to 1 acid for every 2 bases added. Okay? So now, and this has got to do with moles. So now we need to go and see how many moles, it's the acid that's unknown, how many moles of base was added. So if we look at our base, this amount, that volume, and that concentration. So in other words, we have N is, volume, concentration is mole, which is N over V. We know the concentration is 0,5 is equal to N, which is my moles, is what I'm trying to find, divided by my volume, which is, and now here we must be very careful. We do not work in centimeter cubed, we work in decimeter cubed, so we must divide with 1,000. So 0,028, which means that we have N is equal to 0,5 times 0,028, which is equal to 0,0014. Okay, moles. What that tells me is that this many moles was needed to neutralize whatever concentration base acid I had in there. And since it's 1 to 2, Okay, how many acids is 1 to the base 2. For every 2 moles we used 1 acid. What is the moles of H2SO4? Is it double that or half of that?
Double.
Okay, so for every 1 acid we use 2 bases. So in other words, if this is 1 to 2 and we want this one to be 0,0014, notice that this side is half of that side. You see that? So this one must be 0.0007. Okay, so the initial or the amount of moles that is left in here is 0,0007. That's now just before I do that, which means after I added the carbon, calcium carbonate, that is how much I had in here. Okay, now I just want to know how many moles reacted. So now I need to go and see how many moles did I have in the beginning. I know how many moles I have left. That would tell me how many moles reacted. So how many moles did we, because remember we said we have, for this one we have the concentration and volume, which means we can calculate how many moles there was in the beginning. Okay, we've calculated now how many moles was left after this first reaction. So let's see how many moles there was in the beginning. So we have N is C times V. The concentration they said was 1 mole per cubic decimeter. C times V, concentration is 1 mole per cubic decimeter. The volume I had in the beginning, again they give me centimeter cubed, so I must divide with 1,000. That gives me 0,05 cubic decimeters, which means initially I had 0,05 moles in this reaction, in this container. And now how many reacted? How much reacted? How will you calculate how much did react?
Minus what's left from what is there.
Exactly. So 0,05 minus what reacted is 0,0493. Yes. No? Is it 993? I can't see now. The 5 is there. 500 minus. No, it's 5. Yes. Is it correct? Cool. Good. That is how many moles reacted of. So this is NH2SO4. Okay, so we have that the moles that of the the sulfuric acid, moles of sulfuric acid used in this reaction is therefore 0,0493 moles. So if we look at this here, we see that for every 1 mole of sulfuric acid that is used, 1 mole of calcium carbonate is used. Okay, so in order to now see how much of calcium carbonate was used up, we see that for each one, it's 1. So calcium carbonate would have exactly the same amount of moles used. Okay, and now our question is simply, okay, to answer this question, they ask us how many, what was the mass of the calcium carbonate used in the first reaction. And all we need to do now is we know that moles is is equal to mass divided by molar mass. Okay, so that if we want mass, we multiply the number of moles with the molar mass. So we have the number of moles, 0.0493 moles, and now the molar mass. Okay, for calcium, the molar mass is, as you can see here, I don't know if you can see, I think I can zoom. Okay, well, not much. 40. It's 40, so the calcium. For carbon, it is 12, and for oxygen is rounded to 16. So we have, therefore, we have this small again. We have 40 because there is one. Okay. And so we've got 40 for calcium, and then for carbon we have 1 carbon, and then we have 3 oxygens, so it's 3 times 16, and this is 52. 3 times 16 is 48, so that gives me 100, exactly 100, 0.0493 times 100, which gives me a lovely 4.93 grams. So that's the amount of calcium carbonate that was used during this experiment.